Okay, so this problem will be one in linear algebra. And for the purposes of this, we'll be keeping this general to real inner product space. You can imagine that this is just um, to do with like vectors, like ordinary like three-dimensional vectors in space. And so for our vectors, they would be just normal three-dimensional vectors. And then for our inner product, we would just imagine it being essentially equivalent to a dot product. So our problem here is that we have a set of basis vectors, E1, E2, so on up to En, and it's an orthonormal basis for our real inner product space V. Then we have some vector U, some generic vector U in this vector space, V. And then we wish to write U as a unique linear combination of these basis vectors, E1, E2, so on, and so on. And each of these basis vectors is weighted by a coefficient K1, K2, up to Kn. So the indices of these basis vectors and the coefficients match. And we wish to find the coefficients K1, K2, up to Kn. So to do this, we can first start by noting probably the most important piece of information, which is that we have here an orthonormal basis. And what that means is that if we were to take the inner product between any two basis vectors from this set, or essentially the dot product, right? So these angle brackets just essentially denote the inner product or essentially the dot product. So this would be for normal vectors, it would just be equivalent to EI dot EJ. Well, that's just our usual dot product. But yeah, to keep it more general, this is equal to the Kronecker delta, which is equal to 1 when I is not equal to j, and 1 when I equals j. So whenever these basis vectors aren't the same, this inner product, dot product, equals 0. If they are the same, then it equals 1. So essentially these vectors are normalized. They have length 1. So we can see here that this essentially simplifies our problem a lot, because this provides us a way to actually reduce this summation here and just get one term left over. And I'll show you what I mean by that. So we can write this expression here in summation notation as this. Okay, and we can see here that if we were somehow able to introduce the Kronecker delta into this summation, and we sum over I, then all that would be left is the term for which I equals j here. So to get an idea of how we would do this, we see here that the Kronecker delta comes from the inner product between EI and EJ. So let's start by, I don't know, maybe taking the inner product on both sides with EJ. And that's equal to or we could write this less abstractly, more concretely as K1 E1 plus EJ K2 E2 plus so on. And we don't know what any of these actually are equal to, but we can sort of figure it out by noting that the inner product or the dot product is linear with constants. So we can actually pull out any of these constants, right? So if we imagine we have like just in normal three-dimensional space, we have like u dot the vector 3v. Well, since 3 is just a constant here, like these k's are, we can just pull it out the front. So this equals it. Right? And then we just end up with something that we can deal with. So we can do the same here. We can essentially pull out these constants here in this summation. And we'll go back to summation notation. So this will end up being we've basically moved the summation sign outside of this inner product, because you can see here we just sort of get the same thing. So this would just be, if we take these k's outside, we would just have the sum over the k's multiplying ej times ei, and then we just sum those over I. And we see here that we actually end up getting the Kronecker delta from before. So that means that every term in this sum goes to 0. Every single term in this sum goes to 0, except for the one in which I equals j. So essentially what we end up here with is kj. So that tells us that kj equals ej, so it's equal to that inner product. And since this is a real inner product, this is symmetric, so we can just write it as, which tells us that we can write u, the vector u, as this now. We can write it as e1 u e1 plus e2 u e2 plus so on. Right, so this just comes from replacing, so this is k1, k2, k3 from here, and then just replacing them into this up here. And that's it. That's how you get the coefficients in when you have an orthonormal basis for some vector in a vector space.